This last section we're doing in chapter 5 is on complex eigenvalues. So we've seen characteristic polynomials for 2 by 2's where you get that negative under the square root, so we have complex roots. So the mathematics is the same for all this stuff, but you have to know how to do operations with complex numbers. So I thought I'd start with just kind of reviewing, and I call it review because you may or may not have ever seen this before. So it's maybe new to you. So we'll start with, what is a complex number? So I is equal to the square root of -1. And a complex number is something in the form a plus bi. So it has a real part, that a is considered a real part, and the bi is considered an imaginary part. So if you think about the set of all real numbers, complex is even bigger. So like if this is all my reals, complex is all of this. And they use it with a C, usually with a bar. The conjugate of a complex number changes the sign of the imaginary part. So a minus bi and a plus bi are conjugates. If you had a complex number like just 2i, the conjugate would be -2i. Sometimes I like to write a complex number as 2i plus 4. Then the conjugate would be -2i plus 4. So just be careful that it's always changing the sign on the imaginary part. When you want to add two complex numbers, so if I have a plus bi plus c plus di, you add the real components, so a plus c, and you add the imaginary components, b plus di. To multiply complex numbers, so if I want to multiply a plus bi times c plus di, I really am just going to FOIL this out. So I have ac plus bci plus adi plus bdi squared. So notice I have two imaginary parts, and then I squared is -1. So going back up to here, if I is the square root of -1, I squared is -1. So I have AC plus, and I can combine these two, and then it's a minus BD. So if I can combine my real pieces, and then the imaginary pieces. So there are different ways to represent a complex number. So thinking back up to like a plus bi, you can plot imaginary numbers on the real imaginary axis. So if you have a plus bi, you go out to a, and maybe b is here, and that would be a plus bi. So you can use rectangular coordinates, but you can also use polar coordinates. So if we have this rectangular coordinate, a plus bi, what that tells me is that this is a and this is b, because it went a on the real axis, b on the imaginary axis. So I can find this angle by doing, I know that tangent of the angle is equal to b over a. So theta is arctan of b over a. We often call the diagonal or the hypotenuse r, and using Pythagorean theorem, we know that r squared equals a squared plus b squared. So r is equal to the square root of a squared plus b squared. This polar form can come in helpful. It's actually easier to multiply matrices in the polar form. But we won't get into that. We will use it when we do some geometry in a little bit. So we just reviewed kind of complex numbers and how you represent them, how you add them, how you multiply them. And then, so what is C2? All that means is it's a vector of elements from the complex So here is a vector where each piece comes from the complex numbers. All right, so now let's look at the matrix A, and we know that the eigenvalues are 3, so this is 3 plus I and 3 minus I. Again, they will come in conjugate pairs. And I want to find a basis for one eigenspace in the complex plane. We can pick whichever we want. Let's just do 3 plus I. So as before, we have a minus lambda I x equals 0. So I'm going to subtract off 3 plus I off of the diagonals. So 5 minus 3 plus I just subtracting, I get 2 minus I, negative 5, 1, and then negative 2 minus I. You can use the same row reduction techniques. This just gets harder because it's complex. So I'm actually going to write out these equations. We can take either one of these equations. I'm going to take equation 2, and I'm going to solve for x1. So when I do that, I'm going to add over this piece, and I'll get 2 plus I times x2. So x2 is free, and x1 is 2 plus I times x2. So one eigenvector might be 1 and 2 plus I. So we saw what a conjugate was of a complex number. So the conjugate of a plus bi is a minus bi. Similarly, if you have a complex vector, then the conjugate just takes the conjugate of each piece. And knowing this provides a shortcut for finding a basis for an eigenspace. So when the matrix A is real, which all of ours will be, then if you have complex eigenvalues, then they will come in conjugate pairs. So just like we saw in this exercise 1, you have eigenvalues 3 plus I and 3 minus I. Those come in conjugate pairs. The nice thing is the eigenvectors also come in pairs. So knowing this, we can find a basis for the second eigenspace above. So we had lambda 3 is 3 minus I, and a corresponding eigenvector would be 1 and 2 minus I. Those are the conjugates of what we have above. To practice this again, I have another matrix A that acts on C2, so in other words, the eigenvalues are going to be complex. So I have 0.8 plus 0.6i and 0.8 minus 0.6i. Those are my two lambdas. I'm going to find a basis for each eigenspace, so keep in mind I only need to do one. Just subtracting the complex number. 0.5 minus 0.8 is negative 1.3 minus 0.6i, negative 0.6, 0.75. 1.1 minus 0.8 is 0.3 minus 0.6i. And we saw before that we can really take either of these equations. So I'm going to take the second one, 0.75x1 plus 0.3 minus 0.6i, x2 equals 0. So x1 is equal to negative 0.3 plus 0.6i times x2 divided by 0.75. So x1 is negative 0.4 plus 0.8 I x2. So for lambda equals 0.8 plus 0.6i, what a vector could be, my x2 is free, and then I have negative 0.4 plus 8i. And then for lambda equals 0.8 minus 0.6i, I'd have negative 0.4 minus 8i and 1. So we talked about the real and imaginary parts of a complex number. You can also talk about the real and complex part of a vector. So just like we have it split up eigenspaces when you have two free variables, you write it as some vector times x1 plus some vector times x2. Same kind of thing here. We took the real parts and separated them from the imaginary parts. So if we have a 2 by 2 matrix with complex eigenvalues, then we can factor the matrix. Notice that C is not, so this is not a diagonal, so this is just a factorization, not a diagonalization, where P is your real part and the imaginary part, and then your C is of this special form, where your diagonal elements are the same and your off diagonals are opposites. Let's look again at this matrix we saw from exercise 3, and I want to apply a theorem 4 to find an invertible matrix P and a matrix C that is in this form A negative B, B A, such that we have this factorization. So I went ahead and wrote out what my eigenvalue is, and remember the theorem 9 said it had to be an A minus BI form, so A minus BI. So that tells me that A is 0.8 and B is 0.6. So just knowing that, I know that the C is A, negative B, B, A. So there's my C. And the P is made up of the real part of V, where V is the eigenvector. So I labeled that over here. So if I break down this into the real part plus the imaginary part, this would be negative 0.4 and 1, and the imaginary part is negative 0.8 and 0. So this is the real part of V, and this is the imaginary part of V. And so P is made up of those columns, so negative 0.4, 1, and negative 0.8, 0. And then you can check, I just plugged this into my Desmos calculator and did the P and then C, and then P inverse. And notice I didn't calculate the P inverse, I just wrote it like that. So if you let this be A and this be B in Desmos, this would be A inverse. So you can just multiply those and check that it does work. Earlier in the lesson, we reviewed some complex numbers, and we saw that there's a polar form to write this. So if this lambda equals A plus BI, another way to get there is this is our cosine theta, and this is our sine theta. So it could be our cosine theta plus I we saw earlier that r, that radius or the hypotenuse, is that length, and it comes from this square root of a squared plus b squared, and then we can find this angle by doing the inverse tangent, and that's, we have to be careful depending on what our a is. So we're going to use this to analyze matrices that are of this form, A, negative B, B, A, where A and B are both real and both not zero. So if we have this matrix C, in that form, it'll always have eigenvalues of lambda equals A plus BI. So you could check that out. It will always work. And then we want to look at the geometry that this matrix C has on vectors. So going through this analysis, so we first have our C. Well, instead of writing A, I'm going to write R cosine theta, so that's the same thing. And instead of B, I'm going to write R sine theta. Then in this step, I factored out the R. You can multiply by a scalar, or it can be represented by this diagonal matrix. And then we have this cosine, negative sine, sine, cosine, and that is a rotation matrix. So this is a dilation, and this is a rotation. So when you multiply by this matrix C, you're actually rotating and dilating. So if we are given a matrix C that is in the form A, negative B, B, A, which it is, here A is 0.8 and B is 0.6. I'm going to list the eigenvalues of C. Well, I know the eigenvalues are A plus or minus BI. So I have 0.8 plus or minus 0.6i. I want to find the angle of rotation. So because a is greater than 0, the angle is the arctan of b over a, or arctan of 0.6 over 0.8, which is about 0.6435 radians, or about 36.87 degrees. And to find the magnitude, the hypotenuse, it's the square root of a squared plus b squared, so square root of 0.8 squared plus 0.6 squared. I get square root of 0.64 plus 0.36, which is the square root of 1. So that tells me my dilated. It dilated by a factor of 1, so in other words, it didn't dilate at all. And it rotated about 37 degrees.